Alrighty, folks. Well, here we go. Can you believe it? This is the final lesson for Math 30-1. So with this, we will wrap up our final unit, perms and coms. We're going to be using combinations a little bit in this lesson, although we are kind of shifting gears a little bit here to talk about a different application of them, something that we call the binomial theorem. So we'll get into that in a moment. As always, here are the big ideas for today, okay, the important skills we want to come away with and the questions we want to be able to answer. So use that as a little checklist to, check in with yourself after the lesson, after you've done your practice, and see what you maybe need to spend a little more time with or reach out to me about and what you're feeling okay on. All right, without further ado, let's get into it. So we're going to be talking a lot in this lesson about binomials and specifically binomial expansions, what it means to expand a binomial, okay? So before we do that, let's just remind ourselves, what is a binomial? Well, remember, like a bicycle has two wheels, right? A binomial is just a polynomial that has two terms, right? So for example, x squared plus 4. That's a binomial. It has two terms, x squared and 4. Or 3y minus 8, right? Two terms, 3y and 8, okay? Or negative 8, I guess you could call that. 10x cubed, that's one term, minus 4y to the power 4. That's the second term. So that's a binomial as well, right? So in general, how can we represent any binomial? We could just say it's x plus y, right? I mean, it won't always just be an x and a y, of course, as you can see in all of these examples, but it's just two terms being added, and they have to be unlike terms. Otherwise, we could just combine them, and then it's not really a binomial, it's a monomial, right? For example, like 2x squared plus x squared doesn't really count as a binomial because really that's just 3x squared. Although you honestly could do a lot of the stuff we're going to do today with 2x squared plus x squared if you wanted to treat it like a binomial. That would just be more work, though, than combining it into one like term. Okay? So we can also, of course, raise a binomial to an exponent. We've done that lots of times, right? We could have x plus 1 all being squared, right? This binomial is being squared. Now careful, remember, that doesn't mean x squared plus 1 squared. It means x plus 1 squared. So it would really be x plus 1 times itself, right? And then, we would FOIL that out and all that, okay? Or, of course, we could go much higher. We could have 3x minus 5 to the power of 8, right? That would involve 3x minus 5 times 3x minus 5 times 3x minus 5 8 times. Okay, that you can imagine that would not be very fun to multiply all the way out. I mean, it might be fun, but it would take a while, okay? So in general, how could we represent a binomial being raised to some power? Well, x plus y, there's our binomial, to the power of n, right? Some exponent n. So what is the expansion of a binomial? It's just the result of actually doing that, of actually multiplying the binomial out as many times as the exponent indicates, right? So just, again, what we were starting to do there, we didn't finish, but that was starting to actually look at the expansion of 3x minus 5 to the power of 8. If we actually multiplied them all out and collected like terms, we would have done the binomial expansion. So just taking a look at some examples of binomial expansions for the binomial x plus 1, right? For various different exponents, different values of n. So if n is 0, we have x plus 1 to the power of 0, which is of course 1 because anything to the power of 0 is 1, right? So there is the binomial expansion for that one. We actually did what the exponent told us to, right? X plus 1 to the power of 1, well, that's just x plus 1, right? Anything to the power of 1 is just still the same thing. So expanded and simplified, we just get x plus 1, okay? Things get a little more interesting when we move past an n value of 1, right? X plus 1 squared, as we said, that's x plus 1 times itself, right? So foiling that all out, which again, foiling is just making sure x gets multiplied by x, and then x gets multiplied by 1, and then 1 gets multiplied by x, and 1 gets multiplied by 1, because what we're saying here is that these two terms are going to be multiplied by these two terms, so we got to make sure they all actually get multiplied together. If you expand that all out and collect like terms, you end up with x squared plus 2x plus 1, right? X times x, that's where the x squared came from. X times 1 is 1x, and then 1 times x is another 1x, combining those to give us 2x. 1 times 1 is 1, right? That's how we get that trinomial. X plus 1 cubed, That's what this looks like, right? It's x plus 1 times x plus 1 times x plus 1. If you multiply those all out, you end up with x cubed plus 3x squared plus 3x plus 1, right? All that's doing is saying, okay, if we've got x plus 1 times x plus 1 times x plus 1, what are we doing? We're going to do x times x squared, times 1, that's plus x, and then 1 times x, that's another x, plus another 1. So that's the result of multiplying the first two together, and then we've still got to multiply that by an x plus 1, right? We could combine our like terms here before we move on. Okay, and then we would repeat. X squared times x is x cubed. X squared times 1 is x squared. 2x times x is 2x squared. 2x times 1 is 2x, right? Still the same logic, just making sure all three of these terms are getting multiplied by both of these terms. So x squared times x squared times 1. 2x times x, 2x times 1. Now finally, 1 times x is just x, and 1 times 1 is just 1, right? So all we did there was make sure x squared got multiplied by both of these, 2x got multiplied by both of these, and 1 got multiplied by both of these. And if we collect all our like terms, sure enough, we've got x cubed. I see an x squared plus 2x squared. That gives us 3x squareds. And then a 2x plus an x. That gives us 3x plus 1 over there, right? And sure enough, that's what they had here. Just kind of showing you the work that's going on behind that, right? But I mean, we know how to do that. We multiply out our polynomials. If we take x plus 1 to the power of 4, right? Multiply that all out. I won't do it, okay? But hopefully you can kind of see that this could lead us towards something like this, right? An x to the power of 4 now. Again, that kind of makes sense because we've got, you know, eventually we're going to do an x times an x times an x times an x to give us x to the power of 4, right? 4x cubeds, 6x squareds, 4x plus 1. So as you can see, and as kind of just makes sense intuitively, right? If we expand a power of a binomial, the greater the exponent on that binomial, the more terms we end up with, right? Like here we get an x cubed, an x squared, an x, and a constant. Here we're getting an x to the fourth, an x cubed, an x squared, an x, and a constant. You can probably imagine that if n were 5, if we had x plus 1 to the power of 5, well, now we'd have an x to the fifth, and an x to the fourth, and an x to the third, and an x squared, and an x, and a constant term, right? The more multiplications involved, the more terms we end up with in the end. So expanding a power of a binomial gives an expression with more and more terms. The larger the exponent, the more terms we end up with after expansion. Now, viewing this table above, you might even actually already be noticing a bit of a pattern going on between n and the number of terms. Take a look here. When n was 0, we end up with 1 term, just the constant term. When n is 1, we end up with 2 terms. They're actually the same 2 terms we had in the original binomial because we just raised it to the power of 1. When n was 2, we got 3 terms. When n was 3, we got 1, 2, 3, 4 terms. When n was 4, we got 1, 2, 3, 4, 5 terms. Even looking at that example that I just kind of talked about, when n was 5, we imagined having all of these plus an x to the 5th term, right? Giving us 6 terms total. So you can kind of see this pattern here. When n is, whatever n is, we're going to have 1 more term than that when expanded out. So if we have a binomial to the power of 0, we get 1 term. Binomial to the power of 1, 2 terms. Binomial to the power of 2, 3 terms. To the power of 3, 4 terms. To the power of 4, 5 terms, right? So this pattern actually continues on forever. There's always 1 more term than the value of the exponent. So in other words, the number of terms in a binomial expansion is going to be whatever your n, the exponent on the binomial is, plus 1, right? So if you have, you know, x plus y to the power of n, if you were to actually multiply that out, you'll end up with n plus 1 terms, right? So just for an example, x plus y to the power of 96 will have 97 terms, okay? So that's a nice tool to have in our kit to recognize that. Now, of course, as you saw, even just for cubed, I mean, it's not like that was terrible or anything, but it did take, you know, 1, 2, 3, 4, 5 lines of work. Can get easier and easier to make a mistake as things get longer and longer, right? You might miss a like term or miss a negative, stuff like that. So actually multiplying these out can take a while, for sure, right? And it can be very easy to make a mistake. So this is just x plus 1 to the power of 4, right? Here's the work we would have done to just expand x plus 1 to the power of 4. And it's not like brutal or anything. I mean, we could all handle this, but you can see like it's already getting decently long, and there's lots of little opportunities to, like I said, miss a negative or accidentally combine your like terms incorrectly, stuff like that, right? So when we keep in mind x plus 1 is a very simple binomial, right? Like it's just an x and a 1. And again, 4 isn't even that large of an exponent, really. Like in the grand scheme of things, something to the power of 4, that's not that big. So we can see why binomials definitely can get tedious and difficult to expand, right? If you imagine doing the process above for something like 10x cubed minus 4y to the power of 4 to the power of 10, right? Like imagine doing this, but for that multiplied by itself 10 times, you could see that wouldn't, be the most fun thing on earth to do. And you would definitely, it would be very easy to like forget a negative somewhere along the way, or to accidentally combine your like terms, or to apply the power incorrectly, right? It can become very tedious. It can be a lot of work just to expand something like that. Now, luckily, and this is what we're going to be exploring today, mathematicians have found, tested, and proven, important that they've proven that they always work, some patterns in the expanded terms of binomials. And we can rely on these patterns to make things much easier, much faster, and pretty cool too as well, like more interesting to see these connections. Okay, rather than just multiplying and multiplying and multiplying. So let's jump into it. The first thing we're going to talk about here is something called Pascal's triangle. It's very cool. So this triangle was named for a French mathematician in about 1700s, okay, named Blaise Pascal. But actually this triangle has been around for way, way, way longer, long before Pascal was ever born. And even the work Pascal did with it had been well understood long before him. It's one of those situations where, sometimes European mathematicians get the credit for stuff that had been happening other places in the world for long before they had decided to write it down. But the name kind of stuck, and to this day you'll often hear it referred to as Pascal's triangle, okay? But like I said, it's this triangle, and amazingly, as we'll study here, it has a connection to the terms in a binomial expansion. And again, they were actually studied and understood in many parts of the world, including ancient Persia, China, India, for many years before Pascal was born. Actually, the first written record of it dates back to the Persian mathematician Al-Kharajhi around the year 1000, which is about 700 years before Pascal's work. So this is something that we had looked at and looked for patterns in and found the connections to other mathematical concepts long before Pascal ever came along. Still, the name stuck, and we call it Pascal's triangle. So the triangle is actually very simple in its construction. You could actually build this back in elementary school. Grade 4, if you explained how it worked, a grade 4 student would be able to build Pascal's triangle. So all it is, we start with a 1 at the top, and then each row below it is made by adding the two numbers above, the two numbers that it's kind of in between. And you can think of it as having like invisible zeros out here. So like 0 plus 1 is 1, right? These zeros are kind of out here, if that helps you kind of see it, okay? But just let's take a look, right? So we've got 1, the next row is just 1, 1, right? 0 plus 1 gives us 1. That's what we're doing. We're adding those two in between. The next row is where we start to see the pattern a little bit better. Because look, again, 0 plus 1 is 1, but 1 plus 1 gives us 2, right? So in there, 2, it's got a 1 and a 1. That's how we got that 2. We add the two numbers that are it's in between that are above it, right? And then again, 1 plus the invisible 0 here gives us 1. The next row, we can really start to see it taking shape. 1 plus 2, that's where this 3 came from, right? This 3 is 1 plus 2. Same with this one. 2 plus 1 gives us 3, right? Always 1s at the outside because there's always kind of these invisible zeros out here, okay? Let's go to the next row. 1 plus 3 is going to give us a 4 here, right? 3 plus 3 gives us 6. 3 plus 1 gives us 4. 1 plus 4 now gives us 5 in the next row. 4 plus 6 gives us 10. 6 plus 4 gives us 10. 4 plus 1 gives us 5. The next row, okay, if we take a look, 1 plus 5 gives us 6. 5 plus 10 gives us 15. 10 plus 10 gives us 20. 10 plus 5 gives us 15. 5 plus 1 equals 6. Do you think you can challenge yourself to do the next row of Pascal's triangle? Let's try it ourselves. So going to be a 1 out here. 1 plus 6 will give us 7. 6 plus 15 will give us 21. 15 plus 20 gives us 35. 20 plus 15 gives us 35. 15 plus 6 gives us 21. 6 plus 1 gives us 7, and 1 plus 0 gives us 1. And there we go. That's the next row of the triangle. And you could keep doing this as long as you want. Okay? Now it asks us here, do the first 4 rows of Pascal's triangle look familiar at all? So these are the first 4 rows right here. We've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then finally 1, 4, 6, 4, 1. Do those numbers ring a bell? Right? Do you see 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Cool, right? Okay, so this was noticed. It was noticed that the terms in a binomial expansion have coefficients which follow the order of Pascal's triangle. So we're going to explore this a bit, but we're going to switch from doing a specific binomial like we were doing up there with x plus 1 to just a general binomial, x plus y, where x and y are just two unlike terms. Could be anything. Okay, and again though, if we look at doing this, if we do x plus y to the power of 0 equals 1, we get 1, right? X plus y to the power of 1 is x plus y. Look at the coefficients though, 1x plus 1y, right? X plus y squared, if we FOIL that out, we'll get x squared plus x times y plus y times x, or plus 2xy plus y squared. Look, 1, 2, 1, right? X plus y cubed gives us x cubed plus 3x squared y's plus 3xy squareds plus 1y cubed, right? 1, 3, 3, 1 are the coefficients. 1, 4, 6, 4, 1 are the coefficients. 1, 5, 10, 10, 5, 1 are the coefficients, right? This is just Pascal's triangle. If we look at the coefficients on the expanded terms, right? 1, 1, 2, 1, 1, 2, 1. 1, 3, 3, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. Now, I know this kind of seems, almost a little like magical and convenient, and maybe it's just a coincidence, but it actually does make a little bit at least of intuitive sense when we think about it, right? What we're doing by increasing the power on the binomial is adding another multiplication by that binomial, right? This is 4 multiplications of x plus y. This is 5 multiplications of x plus y. And so it kind of makes sense that we would end up with more of these like middle terms here, right? Where there's a combination of, okay, 4 different x's multiplied together and a y, right? That happens 5 times. This happens 10 times. We'll explore that more as we go, especially the connection with that to the idea of combinations, okay? But just intuitively, we can see, well, yeah, I guess multiplying it more times out is going to give us, first of all, more terms and also larger coefficients because there's more combinations of those x times x times x times x times y's that are going to happen, right? Also makes sense that the ends are always going to have coefficients of 1, because if you think about it, the only way to get x to the 5th is from the times where we multiplied the x by the x to get the x squared, and then obviously other terms as well, but then we would eventually take that x squared and multiply it by the x, other terms as well, of course, right? We're doing every term times every term, but then take that x cubed and multiply it by this x eventually to get x to the 4th, and then multiply that x to the 4th eventually by this x to get it 1x to the 5th, right? Where does the y to the 5th come from? Well, doing that for all of the y's, right? Every time you distribute that y times y term from your previous expansion, okay? In the middle, there's more ways to do x times x times x times x times y, right? You could do this x times this x times this x times this x times that y, right? Or then this x times this x times this x times this x times that y, right? And different combinations. In fact, you can come up with 5 different ways to do it, okay? We'll explore that more when we talk about the connections to combinations here. So here are the key patterns that were noticed in the terms of a binomial expansion of x plus y to the power of n that we can rely on to make the analysis of these a lot quicker than actually multiplying them all the way out. So, as we've seen, the coefficients of the terms in the expansion of x plus y to the power of n will match the n plus 1th row of Pascal's triangle, right? And again, that's because really like our expansion starts at 0. So the first row of Pascal's triangle is when we have an exponent of 0. The second row is when we have an exponent of 1. The third row of the triangle is when we have an exponent 2, right? So for example, x plus y to the power of 0 matches the first row, right? It has a coefficient, only one term with a coefficient of 1, right? X plus y to the power of 1 matches the second row, right? This is x plus y to the power of 1, 1, 1, second row of Pascal's triangle. X plus y squared matches the third row, etc., right? 1, 2, 1, 1, 2, 1. That came from when x plus y was raised to the power of 2. Okay, so x plus y to the power of 99 will match the 100th row of Pascal's triangle. Okay, we've also seen how there will be n plus 1 terms in the expansion of x plus y to the power of n, right? Again, we see that pattern here. When n is 4, we have 1, 2, 3, 4, 5 terms. When n is 5, we have 1, 2, 3, 4, 5, 6 terms. Okay. As long as we're ranging it in what we call descending powers of x, meaning we're going to order it so that the exponent on this is the highest, and then it goes down until the exponent on this is the highest, right? X to the power of 5, x to the power of 4, x cubed, x squared, x. That's kind of the natural way to write these. It's kind of our intuitive way of writing it anyway. Like, for example, when we expanded this one, right? X plus 1 times x plus 1. Technically, we could have written it as 1 plus 2x plus x squared, but that would just, I don't know, almost feel wrong, right? We're very used to writing it in descending powers of the first thing there, right? So that's kind of the typical way to write this. So as long as we do that, then we can see that the exponents on x start at n and count down to 0 in each term for the expansion of x plus y to the power of n, right? You can see that here. X to the 5th, well, n was 5. X to the 4th, x to the 3rd, x squared, x, and then x to the 0, right? Don't forget, you can think of this as x to the power of 0, because x to the power of 0, anything to the power of 0 is just 1. And then conversely, the exponents on the second term, on our y, are going to start at 0 and count up to n, right? Again, that's kind of the natural way we would write it. So y to the power of 0, you could think of this term as having, right? Because that's just 1. And then y squared, y cubed, y to the 4th, y to the 5th. Again, kind of just the natural way we write these, right? What's the exponent on 1 on our second term here? It's 1 to the power of 0, right? Then it's 1, okay? Then it's 1 squared, or 1, okay? And then the exponents in each term will add to n, right? And that makes sense as well, because again, no matter what, we are multiplying this out 5 times. So each individual term is the product of 5 multiplications. So it might not all be x to the power of 5, but 5 things, there's been 5 multiplications happening. So x to the power of 5, x to the power of 4, y to the power of 1, right? Well, 4 plus 1 gives us 5. X cubed, y squared. So 3 plus 2 is 5, right? 3 multiplications involving x, 2 involving y, giving us a total of those 5 multiplications of binomials that we would have had to do. 2 and 3 make 5. 1 and 4 make 5. 0 and 5 make 5. Okay? And so recognizing and using these patterns that have been well tested and proven and studied can allow us to not have to actually expand the binomials ourselves in order to find characteristics of the expansion. And as we'll eventually see, even to find like specific terms, not even just like characteristics of the expansion, like how many terms will it have, but actually what the terms themselves are. Let's go ahead and try applying some of these patterns ourselves to see if we can tell some information about some binomials without doing all the work of fully expanding them out. All right, so first up here, it asks us, how many terms are in the expansion of each of the following binomials? So p plus q cubed. Well, remember, it's always going to have n plus 1 terms, right? P plus q to the power of 0 would just have 1 term. It would be 1. P plus q to the power of 1 would have 2 terms. It would be p plus q, 1, 2, right? P plus q squared would have 3 terms. P plus q to the power of 3 will have 4 terms, right? Our n is 3, and it's always going to have n plus 1 terms. What about this one then? X minus 2y to the power of 11, it's going to have how many terms? 12, right? Our n is 11, and it will always have n plus 1 terms. This one, I mean, it wouldn't be terrible to actually expand it out and figure that out on your own, right? But this one, that would not be super fun, right? Multiplying this out 11 times, so it's nice to have that relationship in our back pocket when we need it. Okay, next one here. We're asked what will be the coefficient on the third term of x plus z to the power of 4. Okay, so it's a binomial. It's being raised to the power of 4. Our n is 4 here. So we know that this will have 5 terms, right? But also, we know that the coefficients in the expansion of a binomial to the power of n will match the n plus 1th row of Pascal's triangle, right? Again, that just means here, well, this n is 4, so it will match, or I should say the coefficients match the 5th, which is just the n plus 1th row of Pascal's triangle, right? So what we're thinking of here, we know it's going to have 5 terms, so it's like, you know, something, 1 term plus something, 2 terms, 3 terms, 4 terms, 5 terms. We're interested in what is the coefficient on this term. Well, again, we know that these will follow Pascal's triangle. So like, again, the first row of Pascal's triangle is just a 1. That represents when n is 0. Sure enough, x plus z to the power of 0 would just be 1. So it does have a coefficient, but the coefficient's just 1. The second row matches when we have x plus z to the power of 1, right? And sure enough, it would just be x plus z, 1x plus 1z. When x plus z is squared, we get the third row of Pascal's triangle, 1, 2, 1. Okay, and again, we would know that we would get x squared plus 2xz plus 1z. Okay, now again, just building Pascal's triangle, because we know it matches the 5th row, let's just quickly build Pascal's triangle. We've gotten a good start here. But again, 1, 1, 1, and then 1 plus 1 gives us 2. Next row, 1, 1 plus 2 is 3, 2 plus 1 is 3, 1. And finally, that's the 4th row. We need the 5th row, so 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then a 1 on the outside. So this is the row of Pascal's triangle we're interested in. Sure enough, we can see it has 5 things in it, right? Corresponding to the 5 terms of a binomial expansion that has an exponent of 4, right? Like we said, it should have 5 terms. So the first term will have a coefficient of 1, the second 4, and the third term will have a coefficient of 6. So third term has coefficient 6. Just an aside here that I want to mention it early because it will come up as we go. This works here because of the fact that it really is just 2 variables, right? It's not like 2x, or this isn't like a 4 or something like that. In those cases, the coefficient can contain more than just this Pascal's triangle number, but that's just because you're not just expanding like z, you might be expanding 2z, right? And then like 2z to the power of 4, well, 2 to the power of 4 gives us that 16 term, right? 2 to the power of 4 is 16. So it can be more complicated than just these, but it will still always contain these. We'll do a deeper dive on that as we go, okay? But this one, it really will. The third term will have a coefficient of 6. In fact, we could even work out the third term altogether, not just its coefficient, because we know that the exponents on x, the first thing, start at n and count down to 0. So we would have x to the power of, in this case, n is 4, so this would have an x to the 4th, this would have an x cubed, this would have an x squared, right? Then an x, then x to the 0. Okay, whereas the exponents on the y, that's just the second term, will start at 0 and count up to n. So it would be z to the 0, z to the power of 1, z squared. So in fact, we could even figure out what the third term is altogether. It has a coefficient of 6. It's going to have an x to the power of 2, because 4, 3, 2, right? And it's going to have a z to the power of 2, because 0, 1, 2. So actually, we could figure out that the third term, not only can we figure out its coefficient is 6, we could figure out that it would be 6x squared, z squared. We'll look at that in more detail later as well. So we're going to apply that a bit in this one here. What is the exponent on x in the sixth term of x plus y to the power of 10? What's the exponent on y in the sixth term on that binomial expansion? Okay. Well, again, what's our n? Our n is 10. So it'll have 11 terms, but for what we're interested in this question, right, I'll maybe just write that down. N equals 10, so it has 11 terms. Okay, but also we know that the exponent on x, so the exponent on x counts up from sorry, I have that backwards. Exponent on x counts down. I was thinking ahead a step. Counts down from n to 0, right? Exponent on y counts up from 0 to n. So if we think about it, right, we're going to have something like x to the 10th in the first term, x to the 9th in the second, x to the 8th to the 7th to the 6th to the 5th, and we can just count out where we'll be by the time we get to the 6th term, right? So, right, if we think about it, the first term, like ignoring coefficients, let me just say that, ignoring coefficients, we'll have something like, and I'm going to do more than we really need to do for this question at first, just to show the logic here. Okay, because truth be told, we could just count it out, right? We could say x to the 10th, x to the 9th, 8th, 7th, 6th, 5th, and then when we get to the 6th term, we could figure that out. But just to show you the full logic here, we'll have something like x to the 10th, y to the 0, right? Plus x to the 9th, y to the 1, plus x to the 8th, y squared, x to the 7th, y cubed, x to the 6th, y to the 4th. Always adding to 10 as well, right? We know that. Plus x to the 5th, y cubed, nope, sorry, y to the 5th, x to the 6th, oh my goodness, I keep messing it up, x to the 4th, y to the 6th, plus x cubed, y to the 7th, plus x squared, y to the 8th, almost there, plus x to the power of 1, y to the 9th, plus x to the power of 0, which is just 1, y to the power of 10, right? Now, do we actually need to write all those out? No, but I just wanted to show you the logic here, right? This is how the terms will look. Of course, they'll have coefficients. Those coefficients will match the 11th row of Pascal's triangle, but this is what happens in a binomial expansion, right? We have more and more multiplications of x. We order them in descending powers of x and ascending, meaning going up, powers of y. So if we look at the sixth term here, well, first term, second term, third, fourth, fifth, sixth. That's the sixth term, what we would call T6. T for term, 6 for 6, right? It's the sixth term, okay? So the exponent on x will be 5 in the sixth term. On x will be 5. Exponent on y will actually also be 5. Okay, now again, we don't really need to write that all out. We could have just said, you know, we can just count it out. So 10, 9, 8, 7, 6. This is for x. 10, 9, 8, 7, 6, 5. 1, 2, 3, 4, 5, 6 terms, right? First term, second term, third term, fourth term, fifth term, sixth term. And then for y, starting from 0, 1, 2, 3, 4, 5. And we can see we get the same result there. But just wanted to show, so those didn't just seem like random numbers I was pulling out of nowhere, right? That's the pattern in the binomial expansion. We order them from highest exponent on x to lowest exponent on x, and vice versa for y, which is just the second term in the binomial. All right. Let's now put some of these ideas together and see the role that combinations can play here to make things actually even simpler. All right, so as you know, right, every combination NCR is just equal to some number, right? Like, I mean, for example, 10 choose 2, we could write it that way, but that just equals, I think it's 45, right? That's just a number. 10 choose 2 is a number. So if we think about all of Pascal's triangle, right, it's just made up of numbers, and there's some equivalent combination that could give us those numbers, right? So for example, 1, well, that could be anything choose 0. That's just 1, right? The next row, so like for example, we could write row 1 as like 10 choose 0, and then row 2 as 10 choose 0, 10 choose 0. Right? Now, why would we want to do this? We'll get into it in a second here, okay? But if we rewrite each of the parts of Pascal's triangle as an equivalent combination, what's going to end up happening is that we can find even more relationships that allow us to analyze binomial expansions in even more depth without doing any more work, okay? In fact, even less work than what we've been doing so far. So why though? Why would we ever think to do this? Let's walk through the reasoning here. So we're going to look at the reasoning as to why combinations would even be on our mind here by re-examining what we've looked at a couple times, the expansion of x plus y to the power of n for a couple of values of n. Okay, but we're gonna, to make it really pop, we're gonna, for a couple of these, instead of using exponents, like we'll actually just write out the multiplication. So like instead of x squared, we'll write it as xx, okay? Because that'll hopefully highlight why we're gonna be inspired to use combinations here, okay? So if we look at x plus y to the power of 0, it's just 1. Right? Nothing too much going on there. X plus y to the power of 1 even, not too much to think about there. But things will get a little bit more interesting when we start looking at x plus y squared or x plus y cubed, or obviously even higher powers, okay? So let's look at x plus y squared. What that's going to involve, right? We're going to have x times x to get x squared, x times y to get xy, and then if we think about it, we're going to do y times x to get yx, right? And then y times y to get y squared. And notice what we're doing is we're saying, okay, xy, yx, right? Giving us really two of the same thing because order doesn't matter for multiplication. So xy times and yx are really just both xy, right? Or they're both yx, however you want to look at it. So we combine those to give us two like terms, right? Really what we've got here is the x times the x times the y times the other y times the other x, right? And then y. Okay? Looking at x plus y cubed here. Again, if you actually imagine multiplying these all out, what you're going to get is the x times another x times another x. Again, they're all just x, so yes, that's x cubed. But you can look at it that way, right? It's x1 times x2 times x3. Then we're going to have maybe x1 times x2 times y, right? And then we'll have a x1 times x3 times y. And then maybe we'll have an x2 times an x3 times a y. Now again, those are all really the same thing because x times x is just x squared no matter how you look at it. It's not like they're actually different x's. But you can see there, right? It's like we're looking at the different ways we could choose two x's and one y, right? Do you see how combinations are kind of showing up here? Rather, the different ways we could order two x's and one y, right? Same thing for the y's. You could do x1 times y2 times y3, y1 times x times y3, or y1 times y2 times x, right? Different combinations. Now, those are all equivalent. It's just xy squared no matter how you look at it. And so they all get combined to give us 3xy squared. Okay, so again, it's kind of like we're looking at how many ways are there to choose two x's and a y from three x's and three y's being multiplied together. So this gives us some insight as to why the coefficients in a binomial expansion would follow Pascal's triangle while also showing us how combinations can be helpful. Okay, so for example, the expansion of x plus y squared will have us multiplying x and y together two separate times, giving us both arrangements of x times y, quote unquote, right? It gives us x, y, and yx. Again, that just comes from if we do x plus y times x plus y, we're going to get x times x, x squared, and then we're going to get x times y, right? And then we'll get y times x. and then y squared, right? That's what we're talking about, the two different ways, so to speak, that you can choose to do the x times the y, right? But again, since order doesn't really matter for multiplication, it really gives us two of the same thing, two x times y's, right? The expansion of x plus y cubed is going to have us multiplying x by y 3 separate times, right? Giving us all three arrangements of x times y, right? X times y, x times y times x, and y times x. But again, those are all really the same thing. Order doesn't really matter for multiplication. So do you see the connection to combinations here, right? Yes, those are three different arrangements, okay, but they're kind of all the same thing in terms of multiplication. So what we actually have is three of the same outcome, three like terms. That's why they're going to end up with a coefficient of 3x squared y. Because at the end of the day, these are all just x squared y's. Sure, you can look at them as being ordered differently, but there's three of the same thing. And so that gives us a coefficient of 3 when we collect like terms and simplify. And so this is why mathematicians were inspired to rewrite Pascal's triangle in terms of equivalent combinations. Since n tells us how many times we multiply the binomial, it also tells us the maximum number of arrangements that we will get, right? Since order doesn't matter for multiplication, right, those different arrangements will just become combined to give us the coefficient. So if we take the n, whoops, there should be an in there. If we take the n in x plus y to the power of n and let it be the n in n choose r, right? And then also remember that this corresponds to the n plus 1th row of Pascal's triangle, then we can rewrite the triangle as this, okay? So again, right, 1 is 0, choose 0. 1 and 1 is 1, choose 0, or 1, choose 1, right? 2, choose 0, 2, choose 1, 2, choose 2, right? 2, choose 2 is just 1. 2, choose 1 is 2, and 2, choose 0 is 1. And so again, the inspiration here comes from the fact that, well, really, when we're thinking about that second term, right, 2, choose 1 is 2, but you can think of it as like, again, how many ways are there to choose an x and a y, one from each group, when we multiply these out? Because you could do just giving them numbers here to differentiate. Of course, there's still just x and y, but like you could do x1 with y2, and then you could do y1 with x2. Those both give us xy, and that's why there's two different ways, right? That's why we'll end up with two xy terms, or 2 choose 1. Right? And again, this just carries on, right? 1 could be 3 choose 0, or it could be the 3 could be 3 choose 1. 3 could also be 3 choose 2, 3 choose 3. Notice the patterns here, right? 0 choose 0, 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0. And then as we go this way, 1 choose 0, 1 choose 1. Choose 0, choose 1, choose 2. Choose 0, choose 1, choose 2, choose 3. Choose 0, choose 1, choose 2, choose 3, choose 4, right? And so this kind of arrangements of our terms in the binomial expansion inspired them to rewrite it in terms of Pascal's triangle to see these patterns. So remember, the coefficients in the expansion of x plus y to the power of n will match the numbers in the n plus 1th row of Pascal's triangle. And now we have a quick way to determine a coefficient without writing out the entire triangle. So we just need to think about the relevant row now. So for example, we can quickly tell that the coefficient of the third term in x plus y to the 12, well, it will match the n plus 1th row, right? The n plus 1th row. So we can say it'll be 12, choose 2, which is just 66, right? The third term, why? Because 0, 1, 2, right? 0, 1, 2, 0, 1, 2. So the third term, we're going to do choose 2, right? For any row. And then the 12th row, okay, the 13th row, okay, we'll be doing 12 choose 2, because the first row we're doing 0 choose. The second row we're doing 1 choose. Third row, 2 choose. Okay, so that's pretty quick, right? You don't have to write out Pascal's triangle even, which was already a nice quick way to do it, but we can just tell that the coefficient of the third term in this will be 12 because it's to the power of 12. Choose 2 because it's the third term, okay? So choose 2. 12 choose 2 and it's 66. Boom. Without doing any other math, we know that the coefficient on the third term in this will be 66. Okay, just as a side note here, I'll mention it because it will come up. For binomials that don't just have single variables as their terms, for example, 2x plus y to the power of n, the coefficient won't just be n choose k. We'll talk about k in a second here, because that 2 can contribute to the overall coefficient. But it will still contain that 12 choose 2. More on this soon. Okay, I know that's a lot to think about. I know you might be going like, huh, what? Okay, let's just take a look at how we can actually now pull all of those ideas and those patterns out and use them to come up with a very efficient way of finding any term in any binomial expansion using what we've now arrived at the title of this lesson. We're now ready to talk about the actual full binomial theorem. So here it is, okay? In the expansion of any binomial, x plus y to the power of n, of course, it doesn't always have to just be an x and a y, but these are just standing in for two unlike terms. When written in descending powers of x, meaning highest power on this down to the lowest power on this, the general term, meaning any term that you want to find, is going to be equal to this. So it will be n choose k, x to the power of n minus k, y to the power of k. You can kind of think of this as like a formula for finding any term you want in the expansion of a binomial to any power at all. Okay. Now I know you're probably thinking, k, what's k? Okay. Now it is a formula, but it's a theorem. It's this binomial theorem based on these patterns that we've been looking at and that mathematicians studied and tested and proved. Okay, so let's break down what each part of this formula is actually saying. And this is on your formula sheet, by the way. Small side note, this actually, like if you Google the binomial theorem, it won't quite say this. What it will say, though, is add up all of these from 0 to n, from k is 0 to k is n, because that way we could find the whole expansion, like every term. Typically, we're not that interested in doing that all the time, but we are interested in finding like, the fifth term of this binomial expansion or something like that. And this will let us do that. So what is this? tk plus 1? Well, that's just the term we're looking for, right? Like if we were looking for the second term, if we use this to find, the second term in the expansion of x plus 1 to the power x plus 1 squared, then the second term, we would say t2, the second term is 2x, right? So tk plus 1 is just the term we're looking for, right? For example here, t2 would be 2x, okay? That's the second term of that binomial expansion. What is k? K is 1 less than the term number we're looking for. So for example, if we want the third term, t3, then our k value is 2, right? If we want the 106th term, k is 105, okay? And k, therefore, we can kind of think of k as the place in the relevant row of Pascal's triangle starting from k equals 0. So students get a little thrown off by that at first. They're saying, why isn't it just tk? It's because we start counting from 0, right? And that has to do with the fact that the exponent on y starts at 0. It doesn't start as 1, right? The exponent on y here is 0. X plus 1 squared, 1 to the power of 0 is here. It doesn't start at 1 to the power of 1. So again, looking, right, k is 0 for the first term, k is 1 for the second, k is 2 for the third, k is 3 for the fourth. That's why it's k is 1 less than the term number we're looking for. And then it counts up to k equals n. So just for example, looking at n equals 4, our fifth row of Pascal's triangle here, right? K equals 0, k equals 1, k equals 2, k equals 3, k equals 4, okay? Now n choose k, right here, n choose k, this part, it's at least part of Sometimes it will just be the coefficient, but it's at least part of the coefficient on the term we're looking for. Connecting this with the k numbering above for the combination version of Pascal's triangle, right? If you take a look here, okay, you can see 0 choose k, 1 choose k, 1 choose k, 2 choose k, k is 0, k is 1, k is 2, k is 0, k is 1, k is 2, k is 3. Right? First term, k is 0. Second term, k is 1. Third term, k is 2, etc. So again, it is important to note that the overall coefficient can include more than just n choose k if x to the n minus k and y to the k result in more things to multiply by and simplify, right? So for example, 2x plus y to the power of n, well, that 2 is going to play a role as well, right? If we square 2, we get a 4 involved now, that kind of thing. N is just the exponent from x plus y to the power of n. Now, again, note that this x to the n minus k part here, this x to the n minus k, that makes sense because, again, if k is 0, we're looking at the first term. And we know that the exponent on x starts at n and counts down to 0, right? So again, first term, k is 0, so we'll just have x to the power of n, right? Second term, k is 1, so we're going to have x to the power of 1 less than whatever n was, right? It's counting down. Third term, k is 2, so n minus 2, right? If n is 6, for example, then the first term will have x to the power of 6. The second term will have x to the power of 6 minus 1, or x to the power of 5. Third term, x to the power of 4. Fourth term, x to the power of 3, because k is just increasing by 1 as we go from one term to the next. Okay, the exponent starts on x, starts from n, and counts down to 0 as we move from one term to the next. In other words, as we increase k by 1. Okay, similarly, the y to the k part, this part here in our little formula, this checks out as well, right? Because we know that the exponent on the second term starts at 0 and counts up. Well, k starts at 0 on the first term and counts up from there. So we'll have y to the 0, y to the 1, y squared, y cubed as we move through the terms, term number in the terms of the expansion of the binomial, right? Exponent on y starts from 0 and counts up to n as we move from one term to the next. In other words, as we increase k. Now again, x plus y to the power of n is just the general form of a binomial expansion. X could be anything, y could be anything. It's possible that x and y are more complex than just single variable terms, and we'll need more simplification after applying the binomial theorem. Okay, now again, I know that's a lot of like almost abstract stuff to think about. Let's just try applying the binomial theorem here, okay? Let's see what it's showing us. So we know that the fourth term of x plus y to the power of 5 is 10x squared y cubed. You might be saying, I didn't know that. We looked at it up here, right? The fourth term, so 1, 2, 3, 4, fourth term of x plus y to the power of 5 is going to end up being 10x squared y cubed. You can try foiling that all out if you want and checking and seeing if that really is the fourth term, okay? But let's just see what the binomial theorem tells us. So to find the fourth term, T4, what's our k? Be very careful. What is k for the fourth term? Remember, we start counting from 0. So T1 has a k of 0. T2 has a k of 1. T3 has a k of 2. T4 has a k of 3. Okay, k is always 1 less than the term number. For x plus y to the power of 5, what's our n? Right, our n is just 5. It's the exponent. Okay, so the coefficient should then be, according to this, right, it's n choose k. So the coefficient should be 5 choose 3. Sorry, 5 choose 3. And 5 choose 3, if you put that into your calculator, you just get 10. 5 choose 3 is 10. Hey, this is looking good so far, right? X will have the exponent n minus k, according to this, right? What will be the exponent on x? N minus k. So our n is 5, our k is 3. So the exponent should be 5 minus 3, which is 2. Okay, 10. We found the coefficient to be 10. The exponent on x should be 2. This is looking good so far, 10x squared. And y will have the exponent. Well, what does the binomial theorem say? It says y will just have the exponent k. And k is 3. So putting it all together, the fourth term in the expansion of x plus y to the power of 5, we can see that the coefficient should be 10. X will have the exponent 5 minus 3, which is 2. And y will just have the exponent k. So y will just have the exponent 3. Look at that. 10x squared, y cubed. So it works, right? It works. We've tested out the binomial theorem and it matched the expansions that we looked at earlier. Isn't that a much faster way to figure out what the third term of this, right? Think about what we're doing. Like, that's pretty powerful, right? X plus y to the power of 5, not only have we not had to multiply them all out together, we even know a specific term within this expansion, right? All we had to do was look at these relationships and apply them, okay? And that's the binomial theorem. We're going to now practice it out in a lot of different ways, but that's the core idea at work. Let's try out some examples. Alrighty, so first up here, it wants us to determine the second term in the expansion of p plus q to the power of 5, written in descending powers of p. Okay, so that's the default way we would write it. So determine the second term. What does that tell us? Well, remember, we start counting, right? First term has k of 0. Second term has a k of 1. K is always 1 less than the term number we're interested in, right? And this makes sense. We're looking for T2, the second term, so K must be 1, right? T1 plus 1, T2. In the expansion of P plus Q to the power of 5. So what did we learn? We learned from that. What did we learn about this equation? We just learned that our N is 5, right? N equals 5. We also now know that our x, the first term in our binomial, right, x is p, and our y, the second term in our binomial, is q. Okay? So it really is, though, now okay. We know we're looking for t2, the second term. It will be n choose k. Maybe I'll write it up here where I have a little more room. So t2 will be n choose k. So n is 5. We're looking for the second term, so k is 1. 5 choose 1. Times x to the power of n minus k. Yes, but don't forget, right, this is just the general form. Our x, the first term of our binomial, is really p. So we're going to have p to the power of n minus k. So for us, n is 5, so p to the power of 5 minus k is 1, so 5 minus 1. Times y to the k, the second term of our binomial to the power of k. Well, the second term of our binomial is a q, so q to the power of k is just 1. And there we go, right? All I did there was I took the general term of any binomial expansion, right? This is the binomial theorem, quote-unquote, formula, right? Just based on those relationships we've been looking at. So now all I got to do is figure out what this actually is, what it simplifies to. And so 5 choose 1, we don't need our calculator for that. There are 5 ways to choose one thing from 5 options, right? So 5 choose 1 is just 5. P to the power of 5 minus 1, well, that's just p to the power of 4. And then q to the power of 1, well, that's just q. And there we go. We've now figured out that the second term of this binomial expansion, if I were to actually multiply these all out and collect like terms and write it in terms of descending powers on p, it would just be, the second term would be 5 p to the power of 4 q. Pretty cool. All right, now I've referred to this a few times, but let's see it actually matter in this one, okay? So don't forget, x plus y to the power of n is just a general form for a binomial expansion. The x and the y parts can be other things besides just x and y. I mean, there they were p and q, but they could even be things like, looking ahead a bit, right? Like 2x could be our x. It could be the first term in our binomial, right? Or even a -3. That could be the second term in our binomial, okay? So the x and y parts can need some simplification once you've actually applied the binomial theorem, and that can impact the overall coefficient. So the coefficient will always contain n choose k as one of its like factors, but it won't always just be n choose k. So always be careful, right? If you're asked to find the coefficient, it will contain n choose k, but if there's more going on like there is here, you'll see that the coefficient is actually going to involve that stuff as well. Easier to just see it. So let's try this one out and I'll show you what I mean. So we want to determine the middle term in the expansion of 2x minus 3 to the power of 4, okay? Written in descending powers of x. So let's just think about this. The middle term, what term number is that? If they told us what the term was, we could just start doing this, right? K plus 1, k would be 1 less than the term number, but it said middle term. How do we know what the middle term is? Well, n is 4, right? So this has how many terms? It has 5 terms, right? N plus 1 terms, always, right? So if we think about that, it's going to be, right? It's going to be something, 1 plus something, 2 plus something, 3, 4, 5. 1, 2, 3. Whoops, that's too many. That's 6. Okay. So what is the middle term if there are 5 terms? Well, it's the third term, right? T3 is the middle term. Okay, that's the middle one, 2 on either side. So now we know, okay, we are looking for the third term. So looking for third term, right? We want T3. What does that mean K is? It means K is 2, right? I mean, just look at the formula, tk plus 1. So to find the third term, we'd need k to be 2. We'd be looking for t3 then, right? Which is what we know we are. So k equals 2, okay? And now, think about it. We know n, it's 4. We know k, we figured out that it has to be 2. The only other things we wouldn't like x and y. Well, x and y, our x is just 2x. So we'll have to be careful about that. But x, the first term in our binomial, is 2x. And y, be very careful there. That negative is important. Our y, the second term in our binomial, is actually a -3. But from here, we just need to put the stuff in the right spot, right? So I've written out the formula there as it appears on your sheet. Let's now put in the right stuff. So the third term, the middle term, which is the third term, T3, will be n choose k. So 4 is n, choose 2. That's our k. Times our x, but be careful, right? It's not x, it's whatever the first term is. This is a placeholder, right? So it's 2x, and that's all, including the 2, that is to the power of n minus k. So 4 minus 2, right? Which is 2, I'm sure you can figure out, but let's just write it in to show our substitution here. 4 minus 2 times our y, the second term, but the second term here is a -3. So -3 to the power of just k, right? And k is 2. And there we go. Now all that's left to do is make sure we simplify this correctly. So T3, the third term, will be 4 choose 2. Let's just do that first. If you go to your calculator, you'll find that 4 choose 2 is 6. There are 6 ways to choose two things from 4 options, okay? 6 times 2x, I'm just going to do 4 minus 2 to give us 2, times -3 squared, okay? Let's actually just do those exponents now. So this will be 6 times, okay, 2x squared. Be careful, that's 2x times 2x, right? So we can simplify this a bit. 2 times 2 is 4, and the x times x part will give us x squared. So this is 6 times 4x squared, and -3 squared, that's -3 times -3, which is +9. And we're almost there, but we can do a little more simplification here, right? We've got 6 times 4x squared times 9. So to simplify, the coefficient parts of those, we can just multiply those together, right? So the third term will be 6 times 4 is 24, and 24 times 9 will give us 216. So the third term is 216 x squared, right? The x squared is still there. We were just simplifying by multiplying the coefficients together there. And there we go. We just figured out the middle term of this without ever actually multiplying and foiling that all out, just by applying the binomial theorem. Cool, right? And so notice here, this is what I was referring to, right? N choose k won't always be all of the coefficient. Here we got 216. That comes from the fact that like this 2 being raised to the power of 2 is going to give us a 4, right? This negative 3 raised to the power of 2 is going to give us a 9. So yes, that 4 choose 2, that 6 is part of the coefficient, but there's also this 4 that we're going to multiply it by and this 9. So just be careful. N choose k is part of the coefficient, but it won't always just be n choose k, as we saw in this example here. Okay, let's try one from a diploma. So the coefficient of the 9th term in the expansion of 3x minus 1 to the power of 10, written in descending powers of x, is, okay. So 9th term. What does that tell us? That we need to put into our binomial theorem. 9th term means that k equals 8, right? K is always 1 less than the term number, right? You can always check in with the formula if you forget. How do we find T9? Well, k would have to be 8. That would give us 8 plus 1. We'd be finding the 9th term. In the expansion of, okay, 3x minus 1 to the power of 10. So the x that we're going to put in here, right, the first term of the binomial is 3x. So our x is 3x. And what's our y? The second term, what we're going to put here, it's, careful, it's negative 1. Okay, written in descending powers of x. Oh, and it's to the power of 10, so that is our n. N is 10. Okay, and we're ready to go, right? I've written out the theorem here so we can reference it, but since we're looking for the 9th term, we know that's going to be equal to n choose k. So that's 10 choose 8 for us here, right? K is 8, n is 10, and our x now, so x is 3x to the power of n minus k. 10 minus 8, which is, of course, 2. I'll just write it out here. Okay, really show my work. And then y is negative 1, and we're going to put that just to the power of k, so to the power of 8. And that's going to give us, right, we did most of it now, we just got to make sure we simplify correctly. So 10 choose 8 is 45. Okay, then we've got 3x squared times negative 1 to the power of 8. If we want, we could just do that now, right? Negative 1 to an even power is just going to be 1, right? Any negative number to an even power, because negative times negative is positive, times negative, we're back to positive, times negative, negative, we're back to positive. So it comes out to being positive 1. So the 9th term then is going to be, since it's just times 1, we can leave it out. So we've got 45. Now, careful again, 3x is being squared, right? So see what I mean? Okay, we're doing 3 squared. That's going to impact the overall coefficient. So 9x squared. Now, the multiplying by 1, that's not going to change anything, so if we want, we can just leave it out. But here we go, we're almost done. Now we just got to simplify this out. 45 times 9 can be simplified to 405. So we've got 405 x squared. So there is our 9th term, right? Now, again, notice it wasn't just 10 choose 8. Okay, because again, when you have things that are more complicated than just a single variable, or you've got another number going on here, those contribute to the overall coefficient. 10 choose 8 is in there, 45 is in there, but it got multiplied by 9 as well because our x was really 3x. Okay, but our final answer then, the coefficient is 405. So option D. There we go. All right, one more here, then we'll let you try one out. So determine the term with the largest exponent of x when 2x squared plus x to the power of 3 is expanded. Okay, now this is interesting because both our first term and our second term do contain x's, right? So let's think about this a bit. Which term is going to have the largest exponent on x? Well, again, we know that when written in descending powers of x, the first term, like the first term in our binomial, the exponent on it counts down from n to 0, right? Whereas for the second term, they count up from 0 to n. Okay, so we have to make a decision here because what do we want to maximize? Do we want to maximize the exponent on this or on this, right? When this has the largest exponent it ever has, this will have the smallest exponent it ever has. And when this has the smallest exponent it ever has, this will have the largest exponent because they do opposite things. This counts down from n, this counts up from 0 as we go from one term to the next. Well, if we think about it, right, 2x squared, it's already an x squared. This is just an x. So if we can take this and put it to the power of n, right, take it and put it to the power of 3, we're going to end up with a bigger exponent on that than if we take the 3 and put it on this, while this has an exponent of 0, right? All right, now a quick note that's going to become more important when we start looking at things like finding the constant term, but it applies in all cases. Sometimes, right, your binomial might involve like a fraction where the variable is in the denominator, okay? The binomial theorem still works. We don't have to really change anything about how we think about it, okay? It's just that we now have a negative exponent, right? Because remember, a negative exponent indicates division by the base at the division by the base that many times as opposed to multiplication, right? So for example, like x to the power of 1 would just be x. X to the power of negative 1 is just 1 over x, right? X to the power of 2 would just be x squared. X to the power of negative 2 is 1 over x squared, right? Even here, 3 over 5 x to the fourth is the same as 3 over 5 x to the negative fourth. If that x to the fourth is in the denominator, that's the same as multiplying by x to the negative 4. Okay, now, why are you being reminded of this? Well, negative exponents are usually much easier to simplify than fractions that have a variable in a denominator when doing the binomial theorem. So in general, this is a lot easier to work with than this, even though they are completely equivalent. So for this reason, when we're doing the binomial theorem, we'll just want to rewrite fractions like this as an equivalent expression where the variable has a negative exponent, because then it just comes down to applying the binomial theorem and keeping track of that negative exponent, but nothing changes in how you have to think about it. Okay, let's talk about finding the constant term and more generally, finding a term when we don't exactly know at the beginning which term we're looking for. All right, so let's start out with talking about finding the constant term. Now remember, constants, if there's a variable there, the variable has an exponent of 0, right? Because x to the 0 is just 1, right? So like this is a constant because really it's just 5 times 1 or 5, right? So what we're looking for when we're looking for the constant term is the term that will have an exponent of 0 on the variable, okay? Now, when one term in the binomial is a constant, then the constant term is just going to be the last term or the first term. For example, x plus 2 to the power of 4, the constant 16 will just be the final term, right? Because again, when you imagine multiplying this all out, the last term is just going to be the 2 times 2 times 2 times 2, right? Using our binomial theorem, we could say, oh yeah, it'll be x to the power of 0, 2 to the power of 4, right? Counting down from x to the fourth all the way to x to the 0 for the last term, and 2 to the 0 up to 2 to the fourth on the last term, and 2 to the fourth is just 16, okay? Could also be the first term if the first term in your binomial that you're expanding is the constant. So instead of writing it as x plus 2 to the fourth, 2 plus x to the fourth, the constant 16 will be its first term, right? Our first term would be 2 to the power of fourth. 2 to the 4, x to the 0. The second term would be 2 to the 3, x to the 1, and on and on. But that first term, 2 to the power of 4, x to the power of 0, well, again, x to the power of 0 is just 1. So this is just 2 to the power of 4 times 1, or 16, okay? Now, if both terms contain the variable as a numerator, right, it's not even possible to have a constant term. because every single term in the expansion will involve a multiplication by, I'm using x there, but by whatever our variables are, right? Like if we have, 2x squared plus x to the power of 5, no matter what, when you multiply that out, every single term is going to involve a multiplication by the variable, and therefore it won't have a constant term. They will all contain that variable x, and none of them will be to the power of 0, of course, right? However, when we have a binomial in which both terms contain the variable, but it's in the numerator for one term and in the denominator for the other, there can still be a constant term, right? Because think about that. Like if you're multiplying this x by this 1 over x as you FOIL it all out, right? At a certain point, it's possible that the x times 1 over x just perfectly cancels each other out, and you end up with just a number, okay? However, you can see that it's not going to be the first term or the last term in the expansion. It's going to be somewhere in the middle, right? Because again, the first term of this will be x to the 6th, 1 over x to the 0, right? The last term will be x to the 0, 1 over x to the 6th. Neither of those are constants, right? They both would contain x. So this is because somewhere in the middle, the exponent on this will be the same as the exponent on this, and we'll multiply them together, and then they'll get canceled out, right? So because the variables will have both positive and negative exponents being multiplied together, making it possible for the exponents to cancel each other out and add to 0, right? So just for an example, let's actually look at expanding this one. X plus 1 over x to the power of 6. The fourth term, so when k is 3, if I put in those numbers, okay, just applying the binomial theorem here, T4 is n choose k, so 6 choose 3, times x to the power of n minus k, 6 minus 3, times y to the power of k, and k is 3, right? So 6 choose 3 is 20. 6 minus 3 is 3, so we've got 20x cubed, and then we're going to rewrite 1 over x. Like I said, it just makes it easier to work with as x to the negative 1. Okay, exponent laws tell us if we have x to the negative 1 cubed, that's the same as we can multiply those exponents together. So this is x to the negative 3, right? I mean, that makes sense. X to the negative 1 cubed is 1 over x times 1 over x times 1 over x. So we can see that that's 1 over x cubed, which is just x to the minus 3. So that checks out. Okay. Now, moving along here, see where this is headed? We have x cubed times x to the negative 3. And our exponent laws tell us we can add those two exponents, right? Another way to look at it is this is x times x times x, that's x cubed, times 1 over x times 1 over x times 1 over x. Well, look, x times 1 over x is just 1. X times 1 over x is just 1. X times 1 over x is just 1, right? And the exponent laws back us up there. If we add these two exponents, we get x to the power of 0, which is just 1. And so our constant term is not the first or the last. We see it's actually the fourth term, and it has a value of 20. So in the middle of this binomial expansion, we see the constant 20 show up. Okay, now I just kind of pulled that out of thin air, didn't I? I just said, let's find the fourth term, and I showed you that it was the constant term. But how did we know it would be the fourth term? Why not the third or the second, right? How do we know? We don't actually know which term will be the constant term. I just gave you that, right? We don't know what k is, but can we find it? Yes, we can. And we can use the fact, in order to first find k, what we will do is use the fact that the exponent on the variable will be 0 in the constant term. It has to be, otherwise it's not a constant term, right? If it has x to the power of 1, well, it contains x. Even if it has x to the power of negative 1, it still contains x. It's being divided by x, right? So the only way to get a constant term is if the exponent on the variable is 0. So we can use that fact to figure out what is the correct k to make the overall exponent on our variable become 0. Right? Again, not knowing what the term is the same as not knowing what k is. Because as soon as you know k, you know the term number. The term number is just one more than k, right? If k is 3, we're looking at the fourth term. So again, not knowing what term number just means we don't know what k is. We can figure out what k would need to be, though, to make the exponent on the variable 0. And then, once we've got k, we know everything we need to know to use the binomial theorem to actually determine that constant term. So for example, how did I get that? How did I just figure out that we wanted to find the fourth term? Let's look at it. How could we have determined that the fourth term, k equals 3, was going to be the constant term in the above example? So we can just set up an expression using the binomial theorem, leaving k as an unknown, right? So I mean, what would we do? We would say 6 choose k times x to the 6 minus k times 1 over x to the power of k. Now, all we want to know is how we can get an exponent of 0 on x, right? That's how we figure out what k would need to be, and therefore what term number we're looking for. So we can actually just focus in on the multiplication of the stuff with an x in it. The coefficient stuff is not going to change the exponent on x, right? What I mean by that is we can actually just ignore 6 choose k here, right? The reason being, like if I have, x squared, or I have 2x squared, it doesn't actually matter that the 2 is there, because all we're interested in right now, we will be interested in the overall coefficient later when we want to find the term itself. But if all I'm interested in is what is the exponent on x, well, the exponent on x here is 2. The exponent on x here is also 2. It's just that there's a coefficient of 2, right? Even if I go 100 times x squared, or I guess that's 1,000, right? The exponent on x is still 2, even though there's a big coefficient now. And this holds even when we're, right, even if I'm doing 2x squared versus x squared. Yes, we have a different coefficient here, but we still end up with the same exponent on x. This gives me x squared. Exponent on x is 2. This gives me 4x squared. So yes, it has a different coefficient, but the exponent on x is still 2. Again, even if we do 100x squared, yeah, we have a coefficient of 10,000, but what's the exponent on x? It's still 2. In other words, right, the coefficients don't make a difference to the exponent on x. And to find the constant term, we just need to figure out how to make the exponent on x 0, which is why we can ignore this 6 choose k. If there were a 2 here, we could actually even ignore that. If there were a 17 here, we could ignore that. We just want to figure out how to make the exponent on x 0 as our first step. So simplifying it down a bit, okay, we now know we're starting from something like this, and we just need this to give us x to the power of 0 if we want to get a constant term. So let's set it equal to x to the power of 0 and solve for k, right? Whatever happens when we multiply x to the 6 minus k times 1 over x to the k, we need the result to be x to the 0. So looking at that, right, we're going to rewrite 1 over x as x to the negative 1. That's just a lot easier to work with here, okay? Giving us x to the 6 minus k times x to the negative 1 to the power of k, okay? We want this to equal x to the power of 0. Okay, so now using my exponent laws, negative 1 times k is negative k. I'm multiplying these two powers of x together. So our exponent laws tell us we can add those two exponents. So I'm going to do 6 minus k plus negative k, which is just minus k again. So x to the power of 6 minus k needs to equal x to the power of 0 for us to get a constant term here. 6 minus k is 6 minus 2k, just combining like terms there. And look, we're just using our exponent stuff, right? X to the power of 6 minus 2k. We need that to equal x to the power of 0. Well, that's only going to be true if 6 minus 2k is 0, right? So we need 6 minus 2k to equal 0, and therefore 6 to equal 2k, right? Just adding 2k to both sides, and divide both sides by 2 to figure out that k would need to be 3. Hey, that's what we said, right? I told you at the beginning here, let's just find the fourth term. K will be 3. I didn't tell you how I figured that out, right? But now we know, okay? All we did was figure out, all right, well, we know for the constant term, the exponent on x needs to end up being 0. So if I'm taking x to the 6 minus k and multiplying it by 1 over x to the k, what is the correct k that ends up giving us an overall exponent on x of 0? And then algebraically, we figured out that that would have to be 3, right? We can check our work here. 6 minus k would be 3. 6 minus 3 would be 3. And then if we have x to the power of 3 times 1 over x to the power of 3, we end up with x to the power of 0, a constant. Let's try some examples out like that. All right, so it wants us to determine the constant term in the expansion of 2x squared plus 1 over x all to the power of 3. Now we can see a constant term is possible here because we have x in the numerator, x in the denominator, okay? But we can see also that it's not going to be the first term, it's not going to be the last term. We actually don't know which term it is yet, right? We've got to figure that out, okay? So let's just figure out what we do know. We know our n is 3. We know that our x is 2x squared, and our y, it's 1 over x, but I'm going to write that as x to the negative 1 because that'll be a lot easier to work with, okay? We have to figure out the constant term. So that means we need that the overall exponent on x is x to the 0, okay? Once we figure out the term that happens in, we can figure out that term, right? We would just use the binomial theorem from there. So let's just do that first, right? We need to find the k that causes x to the power of 0 overall, right? So our binomial theorem is this: tk plus 1 equals n choose k times our x to the n minus k times our y to the to just the k. Y to the k, right? So again, for us here though, we can say, like, we can put it all in if we want. tk plus 1 is just going to be n is 3. We don't know what k is, so I'll leave it as an unknown. Our x is 2x squared to the 3 minus k, and our y is x to the negative 1 to the k, right? Now, again, none of this, the 3 choose k, the 2, that stuff doesn't change the exponent on x. It just changes the coefficient in the term. So we will eventually care about it when we're actually finding the constant term. But right now, we're just trying to figure out what would we need the exponents here to be, the k values specifically, to give us an overall exponent of x to the 0. And 2 has no effect on that. 3 choose k has no effect on that, right? So we can just focus in on these parts here, right? We can just say we need x squared to the 3 minus k times x to the negative 1 to the k. We need that to equal x to the power of 0, right? And then yes, there'll be other coefficient stuff going on, but as long as this is correct, the exponent on x will be 0, and we'll have a constant term. So now we're just solving an exponential equation for an unknown, right? We're back in unit 3. So exponent laws tell me I can multiply this. So I'm going to have x to the power of 6 minus 2k, right, times x to the power of negative k, that's negative 1 times k. That needs to equal x to the power of 0. Just going to move up here a bit. Now I'm multiplying these two powers of x together. Exponent laws tell me I can add their exponents. So this is x to the power of 6 minus 2k plus negative k. So minus k needs to equal x to the power of 0. And just simplifying a bit here, 6 minus 2k minus another k, that's 6 minus 3k. That needs to equal x to the power of 0. And therefore, right, if x to the power of 6 minus 3k equals x to the power of 0, well, that's only true. That can only be true if 6 minus 3k is 0. So add 3k to both sides. We need 6 to equal 3k. Divide both sides by 3. We need 2 to be k. So k is 2 for the constant term, right? What we've just figured out is that if k is 2, the overall exponent on x comes out to be 0, meaning it's just x to the power of 0, it's 1, right? And then all the other coefficient stuff is going to be what makes up the rest of that term. It's going to be multiplied by x to the 0, which is 1, giving us a constant, okay? So we need to find the, if k is 2, we need the, which term number? Third term, right? So it's the third term, T3, okay? So there we go. Now we know what we're finding. To find the constant term, we now know that we are trying to find T3. This should be the constant term because we figured out that when k is 2, the overall exponent on x is 0. All right, so now we're going to actually use the full binomial theorem. We are concerned with the coefficients now because we're actually trying to find the term, right? We're not just figuring out what term number would have an x to the 0, okay? So we're trying to find T3. It's going to be equal to n choose k. Let me just write the binomial theorem up here so we can reference it. N choose k, x to the n minus k, y to the k. So n choose k, our n is 3. We now know that the k will be 2 for the constant term. So 3 choose 2 times x. Be careful, our x is not just x, it's 2x squared to the power of n minus k, so 3 minus 2 times y. Our y is 1 over x, or x to the minus 1, to just the power of k. Well, our k we established is 2. So the third term will be, whoop, cat is meowing. 3 choose 2 is just 3, right? There are 3 ways to choose 2 things from 3 options, right? You're just leaving one out. And then here we've got 2x squared to the power of 1, because 3 minus 2 is 1. And then x to the negative 1 times 2, that's just x to the negative 2. So the third term will be, okay, 2x squared to the power of 1 is still just 2x squared. And then multiply that by x to the negative 2. This is the nice thing about finding the constant term is we know what we're supposed to get, right? We're supposed to end up with x to the power of 0. I'm liking this, x to squared times x to the negative 2, right? That's just going to be x to the 0. So simplifying this a bit, 3 times 2 will give us 6. And then x squared times x to the negative 2 gives us x to the power of 0. So this is just 6. And hey, we were looking for a constant. We found a constant, right? The third term is just 6. No x's attached, right? Because again, this is just 6 times x to the 0. Multiplying these two powers of x, we can add the exponents. 2 plus negative 2 is 0. That's what we were trying to do here, and we've confirmed for sure now that it does work out. So our third term, the constant term, is just 6. So just an extra step here, really, where first, okay, we don't quite know what k is right off the bat, but we can figure it out. Okay, let's try another one here. Determine the term independent of x. Okay, that's just another way of saying the constant term, right? Constant means it's independent of x, right? Like 3x is dependent. The value of this, if I asked you how big is 3x, you would say, well, it depends on x, right? If x is 1, then this is 3. But if x is 2, then this is 6, right? However, if I asked you how big is 3, you would say it's 3, right? There's no such thing as, oh, it depends on how big x is, right? If we look at an actual binomial, x squared plus, or trinomial, I guess, plus 2x plus 1, right? And I asked you, how big is this term? You'd say, well, it depends on what x is. How big is this term? Well, it depends on x, right? How big is this term? That doesn't depend on x. That's 1, no matter what x is. So that's what independent of x means. It's another way of saying the constant term, okay? Constant. That's why it's constant. It doesn't vary when we vary x, which is the variable. Constant term. We need x to the power of 0. right? So in the expansion of this guy, 2x minus 1 over x squared to the power of 15. Okay, so we know our n is 15. That's good to know. But again, we don't know what k is because we don't know what term we're looking for. If it told us it was the fourth term, we would know, okay, k is 3. But we don't. The constant term is somewhere in the middle there. So that's our step one. When we're not actually sure what term we're looking for, that just means we're not sure what k is. I should say we're not sure what term number we're looking for. We know we're looking for the constant term. We just don't know if that's T3 or T4 or T6 or T7. Who knows? Okay. So first, we need to find the k to give, or to cause, I guess, find k to cause the overall exponent on x to be 0. Okay? So here we go, right? We know that tk plus 1 equals n choose k times whatever the first term is to the power of n minus k times whatever the second term is to the power of k, right? So for us, we know that's going to be 15 choose k, don't know what k is. Our x is 2x to the power of 15 minus k. And our y is 1 over x squared, but I'm going to rewrite that as x to the negative 2 to the power of k. Okay, now again, does this change the exponent on x? Even this 2, does that change the exponent on x? Right? No, it just changes their coefficient, right? Again, x squared is x squared. 2x squared is 4x squared. The exponent on x is 2 either way, right? No matter what I make this coefficient, the exponent on x still comes out to be the same thing. So since we're just worried about how to make the overall exponent on x come out to be 0, we can just ignore these, right? So what we're really interested in here is, okay, the fact that we have x to the power of 15 minus k times x to the negative 2 to the power of k. And we need that to come out to give us overall x to the power of 0 in order to find our constant term. So let's just work on now solving this exponential equation, right? Notice the only thing we don't know here is k. We can solve for k. Well, we also don't know x, but we know when solving an exponential equation, we can still work with that because we'll get it so that we have x to the power of something equals x to the power of 0, and then we know that that something must equal 0. So here we go. We've got x to the power of 15 minus k. If we multiply that by x, okay, x to the negative 2, all being raised to the power of k, our exponent laws tell us we can multiply those two exponents together. So negative 2 times k is negative 2k, and that equals x to the power of 0 for us to have a constant term. Now, exponent laws tell us we're multiplying these two together. They're both base x, so we can add their exponents. So this is x to the 15 minus k plus negative 2k. So subtract 2k will equal x to the power of 0. And this means that x to the power of 15 minus 3k, right? Negative k minus 2k gives us negative 3k. And there we go, right? So x to the power, we need x to the power of 15 minus 3k to equal x to the power of 0. Well, when can that happen? If and only if 15 minus 3k is 0. So add 3k to both sides, divide both sides by 3, and we get that k needs to be 5. So we're expecting our constant term to happen when k is 5. Which term number is that? It is the 6th term, right? So it's the 6th term. We're looking for T6, right? So the constant term should be T6 if we did that correctly. So what's left to do? Go ahead and find T6, because then we'll be finding the constant term, or the term independent of x, which is what we were actually trying to do to solve this question. So step 2, let's now find T6. That should be our constant term. So if we're finding T6, what's our k? I mean, we already figured it out. k will be 5, right? K is 1 less than the term number we're interested in at the moment. So T6 will be, okay, just going to reference the binomial theorem over here. N choose k. Our n is 15, k is 5, times our x, be careful, our x here, the first term in a binomial we're expanding is 2x, to the power of n minus k, so to the power of 15 minus 5, which is 10. Okay, I'll just write it in for now as 15 minus 5. Now our y, we got to be super careful here. I actually made a mistake there when I wrote it down. It's not really x to the minus 2. Be careful. It's negative x to the minus 2, right? We're subtracting this term. So I didn't really include that here. Luckily, it doesn't matter because, again, of what we talked about, the coefficient doesn't make a difference to the exponent on x. But now it will make a difference. We got to be super careful here. So I need to make sure I put in a negative x to the minus 2 as our y. Okay, and then the y in the binomial theorem is just to the power of our k, which we know is 5. So to the power of 5 there. Okay, so moving on here, we've got that the sixth term, 15 choose 5 is just 3003. That's one we'd need our calculator for probably. Times 2x to the 15 minus 5, so that's 2x to the 10, like we said. And then here, we've now got, okay, let's think about this, right? We have a negative x to the minus 2 being raised to the power of 5. So we know that we can multiply that negative 2 by that 5 to get this is x to the negative 10. But is it negative x to the negative 10 or x to the negative 10? Well, we have a negative being raised to an odd power. So that's going to stay negative, right? Like negative 1 cubed is negative 1 times negative 1 times negative 1. When we have a negative to an odd power, negative 1 times negative 1 is positive 1, times negative 1 gets us back to negative 1, right? Whenever we have an odd exponent on a negative base, we get a negative result. So we have to be careful here. This negative is going to be with us still. We're going to have negative x to the power of negative 10. Okay? All right. So let's just keep simplifying here. The sixth term will be 3003. 2 to the power of 10 is 1024. X to the power of 10 is, of course, just x to the power of 10 times this negative x to the negative 10. All right, almost there. We can just do a bit more simplification. Let's just multiply all our coefficients together. So we've got the 3003 times the 1024 times the negative 1. So that's going to give us negative. Now, 3003 times 1024 is a big number. It's 3,075,072. Okay, and then what have we got left? We've got our x to the 10 times our x to the negative 10, right? A free little work check along the way. We were trying to find a constant term. Now we're going to get a constant term. X to the 10 times x to the negative 10, right? Exponents get added, so this is x to the 0, which gives us a constant. So our sixth term is just going to be negative 3,075,072. That negative, see, that was important. If we had forgotten that our y was actually negative x to the minus 2, we wouldn't have had that negative there in our final answer. So we got to be careful. All right, but there we go. All right, so the last thing we're going to talk about here in this lesson, and therefore in this unit, and therefore in Math 30-1, is actually not something new. It's when k is unknown. Well, you think about that, that's what we've been doing with the constant term, right? When k is unknown. So it's just whenever a question is asking you, like, which term, right? Well, if it's asking you which term, it means we don't know what k is. Because if we knew what k was, we could say what term number we're looking for, right? If we say k is 5, we know that we're looking for the sixth term. So usually the first thing we need to do is just figure out what k is. Because in order to figure out what the term is, we first need to know what number term it is, and then we can just use our binomial theorem, right? If we don't know what the term is, like if we don't know what k is, we don't know which term we're even trying to find in the first place, let alone what the term itself will be. But once we know what the k is, we can just use our binomial theorem to figure it out, right? Once we know what k is, the binomial theorem sorts out what the actual term itself is. But first, we have to figure out what number term is it. Is it t1, t2, t3, etc.? So like we were doing with the constants, first, write out the binomial theorem, leaving k as an unknown, and that just makes it easier to think about or algebraically solve for what k would need to be to give us the desired characteristics of that unknown term. Let's try it out. You'll notice, though, it really is the same idea as the constant term. It's just now we might not want it to have x to the 0. Maybe we want it to have some other power on x or, some other variable that's involved in our binomial. Let's give it a shot. So first one, determine the term that contains a to the power of 7 in the expansion of 3 minus a to the power of 10. Right? So see what I mean? It's just not telling us, oh, find the third term. It's saying find the term that contains this. So you can see how this just boils down to, all right, we just need to figure out what k is, right? And then we can use our binomial theorem to solve for what the actual term itself is, once we know what its k value is. So a couple ways we could go at this. I'll algebraically solve it, but note that we could take advantage of the fact that, well, a is the second term in the binomial we're expanding, right? It's like the y, okay? And we know that those count up from 0. So we could actually figure out that this should be the 8th term, right? 0, 1, 2, 3, 4, 5, 6, 7. So it will be the 8th term with a k value of 7. We could reason it out that way, okay? But we could also just, again, jump in and say, okay, let's find the k that will find k to cause a to the power of 7, right? We know that k plus 1 will be equal to n choose k. Our n here is 10. So 10 choose k times our x, which is just 3 to the power of 10 minus k, times negative a to the power of k, right? And we want a to be to the power of 7. So honestly, just looking at this, we can see, oh, okay, well, that's going to happen when k is 7, right? So we need k equals 7 to have an a to the power of 7 in that term, right? There'll be other stuff, of course. All of this will be going on, but that's all it took to figure out what we need k to be, right? And again, we could have relied on the fact that it would start out with an a to the 0. The next term would have a to the 1, then a squared, then a cubed, right? But writing it out here, we can also just pretty quickly see, what do we need k to be for a to have a power of 7? Well, we need k to be 7. That's our second term, and that just gets raised to the power of k. So what term number are we looking for? We're looking for the 8th term, like we predicted, okay? The term number is always one more than the k value. So here we go. Now we know that it will be the 8th term. All that's left to do is find the 8th term. So again, k plus 1 equals n choose k times our x to the n minus k times our y to the k. So just plugging in for this binomial expansion, now we know we want t8. Our n is 10, so it's 10 choose. We know that k is 7, okay, for the 8th term, times our x. Be careful, our x is actually 3 to the power of 10 minus 7, right? I might just skip a step there and write in 3 times y to the power of k. And be careful, our y is not a, our y is negative a. And that's being raised to the power of k, which we figured out is 7, in order to get an exponent of 7 on a. And we'll be able to check our work the same way as we did with the constants, right? We're trying to find the term that contains a to the power of 7. So once we find this term, it better contain a to the power of 7. It's looking pretty promising. There's going to be some coefficient stuff going on, but we can tell that the exponent on a will indeed be 7. So the 8th term then is 10 choose 7, which is just 120, times 3 to the power of 3, which is just 27, 3 times 3 times 3, times, well, negative a to the power of 7, that's just negative a to the power of 7. Notice I'm keeping the negative because we have a negative to an odd power, right? If this had been an even power, we would have lost that negative, but it's not. It's odd. So now all that's left to do to simplify is just multiply all those coefficients together to give us that the 8th term is 120 times 27 times negative 1 times a to the power of 7. So 120 times 27 is 3,240 times negative 1 makes it negative 3,240 times a to the power of 7. And there we go. And we're feeling pretty good because we found a term that does contain a to the power of 7, which is what we were asked to do, right? So all that we had to do first was figure out what k needed to be. From there, it's a good old binomial theorem calculation. Let's move on to this one. So this one asks, which term contains x to the 4th, y cubed in 3x minus y to the power of 7? Now, honestly, you can kind of just see here, right? We've just got an x and a y here, so what would k need to be? I mean, looking at our binomial theorem, to end up with the second thing to the power of 3, it just gets raised to the power of k, so we can kind of just see that our k is 3, right? We can make it pop to ourselves a little bit more by writing out the binomial theorem. Find k to cause x to the 4th, y cubed. But the k plus 1th term will just be, for us, n choose k, n is 7. So 7 choose k times x. Our x is 3x. Again, the 3 isn't going to have any effect on the exponent on x. It just changes the coefficient. To the power of, okay, so 7 minus k times our y. Our y is negative y to the power of k, right? Now, again, we want x to the power of 4, y to the power of 3. That's what we're looking for. So we can take a second and think about it here. How do we get that? Well, y to the power of 3, we would need k to be 3, obviously, right? And x to the power of 4, well, 7 minus 3 would be 4, right? So we just need k equals 3. Looking at it like this just makes it even more easy to pick out, right? If you can recognize it here as well, that's great. But writing it out as a binomial theorem with k as an unknown really makes it easy to pick out, right? So we just need k to equal 3, right? To get x to the 7 minus 3, which is x to the 4, right? That's what we want. And y to the k, y to the 3, which is what we want, right? Y to the 3. Okay, x to the 4th, y to the 3rd. Looks like making k 3 is the way to go. So we now know we are looking for which term number? If k is 3, the 4th term, right? T4. So all that's left to do is actually find T4. We know that the 4th term will be where x to the 4th y cubed shows up. We just got to figure out what that term actually is now. So the 4th term will be 7 choose k, or n choose k, but n is 7. We know that k is 3, so we've got 7 choose 3, times our x, which, be careful, is really 3x, to the power of n minus k, so 7 minus 3, that's 4, times our y, again, be careful, our y is not y, it's negative y, to the power of k, and k is 3. So let's just simplify now. The 4th term will be 7 choose 3 is 35. 3x to the power of 4, so that 3 is getting raised to the power of 4, right? So we have 3 to the power of 4 is 81. And then x to the power of 4 is just x to the power of 4. Now, negative y cubed. What do we end up with? Do we end up with y cubed or negative y cubed? Right, we're going to get negative y cubed. A negative raised to an odd power is still negative. So we get negative y cubed. Okay, and now we're really getting there. We just got to multiply all those coefficients together to simplify. So we got to do 35 times 81 times negative 1. That gives us negative 2,835. And then we've got this x to the 4th and this y cubed. Okay, and there we go. that's what we wanted. We wanted x to the fourth y cubed. So I'm feeling pretty good about that now. We definitely got what we were supposed to be finding coming out. So unless we made some little math mistake somewhere, that should be the fourth term, and it should be the term that contains x to the fourth y cubed. Again, worth noting that we could have also figured it out with kind of our counting stuff here, right? X, we know that the power on x is going to count down from n. So 7, 6, 5, 4, that's the fourth term. It's also going to count up from 0 to n on the second term. So 0, 1, 2, 3. Again, the fourth term, checking it both ways. But there we go. All right, last example of Math 30-1. So it says here, given that a term in the expansion of ax minus y to the power of 6 is negative 252xy to the fifth, determine the numerical value of a. So a little bit reversed here, right? They've actually given us what the term is, and we have to figure out what the binomial that we started with must have been. Okay, so again here, we don't quite know what k is, do we? Right? Like I said, when we don't know what k is, that's basically our first step. Figure out k. Because how do we figure out, we have a term, but we have no idea what term number it is. And all of the binomial theorem is based on knowing what term you're looking for, right? Or what, in this case, reversed, knowing what term we have, right? So let's take a look here. What would be our k? Can you pick out what k would be, right? Well, x, the power on x is 1. The power on y is 5. We're not dealing with any weirdness here. It's not x squared or y cubed or anything like that in our original binomial. So our k must just be 5, right? That would work because we would have, for the fifth term, right, it's y to the k, right? It's y to the k, so if k is 5, we would end up with y to the 5, right? And then for x, it's n minus k. So if k is 5, we would have 6 minus 5, which is 1, which is the exponent we see on x here. You could also use that counting method, right? 6, 5, 4, 3, 2, 1 for x, or 0, 1, 2, 3, 4, 5 for our y. So we can see here, that k equals 5. Right? Again, if we wanted, we could write out the binomial expansion thing and see what that gives us. Okay, but we can see that our k is 5. So what do we know? We know then that T6 is negative 252 xy to the fifth. Okay, so with that in mind here, let's just see what we can say. We know that T6 will be n choose k. We can see that our n is 6. So 6 choose, and we can work out that our k is 5. 6 choose 5 times our x. Now what's our x? It's ax. We don't know what a is, but whatever it is, we do ax to the power of n minus k, so to the power of 6 minus 5, times our y, the second term in our binomial, which is negative y, to the power of k, which is 5, right? And we also know that T6 is this, right? This is the sixth term, right? So in other words, we can take this whole thing again, but make the left side just be negative 252 xy to the power of 5 is equal to, again, 6 choose 5 times ax to the power of 6 minus 5, I'll just write that as 1, times negative y to the power of 5. And look at this, right? We can see that we don't know a still, but this is just a number, right? We don't know x or y. Again, they're just variables. We could put whatever we wanted in as x and y, but remember, this is supposed to be the same as this, so we can kind of see that our x and our y should end up just canceling out. We should be able to end up solving for a here. Let's just keep following this and see where it leads us. So we'll have negative 252 xy to the fifth equal to, okay, 6 choose 5 is just 6, right? Ax to the power of 1 is just ax. And then negative y to the power of 5, is that y to the 5 or is it negative y to the 5? It's negative y to the 5, right? A negative number to an odd exponent is still negative. Okay, do you see how this is looking promising, right? If I want to solve for a, I can see I'm eventually going to divide by x. That'll cancel out. I'm eventually going to divide by y to the 5th. That'll cancel out. So it looks like a is pretty solvable here. So negative 252 xy to the 5th equals, let's just multiply together to simplify a bit here. I'm going to have negative 6a xy to the power of 5, right? 6 times a times negative 1. Negative 6a times xy to the power of 5. Now we're solving for a. Right now a is being multiplied by negative 6 and by xy to the power of 5. So let's just divide both sides by negative 6 xy to the power of 5. Negative 6 over negative 6 is just 1, x over x is just 1, and y to the power of 5 is just over y to the power of 5 is just 1. Do that to this side as well. Can't just divide one side by something. And look at that. We've got x over x is just 1. Y to the 5th over y to the 5th is just 1. And that means that our a is just equal to negative 252 over negative 6. Which, if you put it in your calculator, negative 252 is actually divisible by negative 6. It didn't have to be. There's no reason this a couldn't have been a fraction. But it does end up just giving us positive 42, right? And so it's the same process. We just kind of worked backwards here. In this case, we actually knew what our term was. We were trying to figure out what one of the things on this right side would have needed to be. Okay, but using the same formula, using that binomial theorem formula, and kind of working backwards from already knowing the term number. And so with that, we are finished the notes and examples for the entire course of Math 30-1. Hard to believe that we are through it already. Okay, so go ahead and try these ones out while it's fresh in your brain, and then of course you can do the rest of the practice for this binomial theorem stuff and get comfortable with it. Make sure you're reaching out to me with any questions, any concerns, book a meeting for all that kind of stuff, right? Concepts or examples that you got stuck on. I'm always happy to help. And with that, all you have left to do now is your topic 2 quiz for this unit, as well as the final unit test for unit 5, perms, comms, and the binomial theorem. And then it's time to start preparing for the diploma. So you will find in the Google Classroom a lot of resources aimed at diploma review. Okay, of course, for that as well, reach out to me with any questions or concerns. Okay, and yeah, thank you so much for a great quarter in Math 30-1. It's been a pleasure. And reach out to me, like I said, book a meeting, whatever it is, if you want to go over it. And there we go. That's it.